Hey, welcome back to Fat Mama Physics. In this video, I'm going to introduce to you the idea of the net force and as well as free body diagrams. I assume that you already know Newton's second law, which is Fnet equals to ma. So let's get started. First of all, when we draw free body diagrams, we need to know what a force is. It's a push or pull on an object caused by some sort of interaction. It doesn't have to be in contact. It could be not in contact, for example, gravity. You don't have to be touching anything to feel the force due to gravity. And the other thing is that forces, we use the units newtons for Sir Isaac Newton that discovered, or the for Sir Isaac Newton who came up with his three laws. The forces that we will deal in this unit are in this table. You can read it yourself. Today I will only talk about a few and will not go into detail in any of them. Force of gravity, some sort of applied force or push, friction, some sort of reaction force or something pushing against you, and air resistance, okay? Let's do a few free body diagrams to get us started to see how we draw them. Before you do any problem, it is a must that you draw a free body diagram. Now sometimes, yes, sure, they're worth marks, but the most important thing is that it helps you conceptualize the problem. It also helps you to do the calculations in the problem by visualizing the direction of the forces. So how do we draw them? First of all, let's do an example along with the steps used. Here, Amazon delivery box. You probably had many of them coming along your way. So whenever you have an object, it's the easiest just to draw a box, even if it's a person or whatnot. And it's resting on a table, so I'm going to draw a table here as a flat line. But the important thing here is my box. That's my system that I'm interested in. I'm going to put a dot in the middle of my box. I'm assuming the mass distribution is even in the box, and if it's not, if you could find an object center of mass. The object center of mass is kind of like the balancing point. If I had to balance this object on a needle like that, it would stay upright. It's kind of what that is. Next up, we want to identify and draw all forces acting on this object using arrows away from this dotted dot here, and it must point away from this dot. So don't draw an arrow over here or there. Start it from the dot, okay? The length of the arrows should represent the magnitude of the force. So the directions for the direction, length is for the magnitude. Here we have an Amazon delivery box resting on the table. Now, like I said before, no matter where your object is, as long as this object is on Earth, it always experiences gravity. If this box didn't experience gravity, it would probably be floating somewhere already. So I'm going to draw a line away from this box and the arrow at the tip. And length is relative. Right now I have nothing to compare it to, so that's my length. And the force due to gravity, if you've seen it here above, it's F sub G. Now that's not the only force acting on this box, is it? I mean, if that was the only force acting on the box, it would probably fall through the table. The table is doing something to hold the box up, otherwise it would be moving. So I'm going to draw a line here, and because this box is not moving, I need to draw an arrow that's probably equal in magnitude to the force due to gravity. So the two forces balance out, causing the box just to rest on the table. So that's the force here that the table exerts on the box, which I'm going to label it the normal force. More on normal force later, but you just kind of have to take my word for it. Sometimes it's called the reaction force or the R. Next up, number 2, we have a mosquito falling at terminal velocity, apparently, so it must have died somehow. Here I'm going to draw a mosquito. You can draw a box. It doesn't matter, just for effect. So a dot in the middle of the mosquito, just where I'm going to draw my arrows coming from there. The when you're falling at terminal velocity, this is when your force of gravity acting on you is balanced by the force due to air resistance or drag forces acting on you so that you are no longer accelerating downwards, okay? You're falling at a constant velocity. So that's your terminal velocity. These two forces also balance. In fact, I can just put like two arrows like, notice my two arrows are roughly equal in length. Okay, next up we have a phone being thrown up as it just leaves the hand. So let's draw a hand here. And the phone, well, it just leaves the hand. My phone is the object of interest, so I don't care about the hand really. I just care about the phone. I'm putting a dot here in the middle, and notice it's no longer touching the hand. That's kind of important there. Okay, so obviously if it's on Earth, it's has the force of gravity acting on it. Okay, and as it's being thrown up, you might think that, well, if it's being thrown up, shouldn't there be some upward force acting on the phone because the person threw it? The important thing here is the phone has left the person's hand, no longer in contact with the person's hand. The hand cannot exert more force on the phone already. It's moving as it is moving now, and the only thing that could affect it is the force due to gravity. Now, if you're thinking, well, shouldn't there always also be air resistance? And yes, you are right. If the phone is moving upwards, then the drag force or the air resistance should be against that motion. So there's some air resistance downwards. Okay, so that's the most you can draw for this particular phone diagram. The last but not least, we have a kangaroo sliding across ice and slowing down. Okay, so that's, imagine you are going across the ice and you're not pumping yourself and you're just feeling the ice flow. That's my crappy drawing of a kangaroo with a little pouch there. So I draw the dot here at the center of gravity in the middle of my kangaroo roughly. So we do know there's always still gravity acting on the kangaroo. Because he's sitting on a surface, it doesn't matter what surface, there is still an upwards force acting on the kangaroo to keep the kangaroo falling through the ice, and that's your normal force or reaction force the ground has with the kangaroo. But the kangaroo is sliding forward while slowing down. So if you're thinking about the force of friction, you are correct, acting on the kangaroo in the backwards direction, opposing motion, kind of like air resistance. And that's the one causing the kangaroo to slow down. If you're thinking, oh, well, isn't the kangaroo doesn't have a applied force or some sort of force pushing the kangaroo forward? Well, if there's nothing touching the kangaroo, there's nothing pushing the kangaroo, nothing pulling on the kangaroo, then there is no applied force on this kangaroo. The moving forward is just the fact that it's moving forward has nothing to do with the force. It's just the kangaroo's momentum is already in the forward direction, and the forces are kind of chipping away at the kangaroo's momentum, its motion moving forward. Now, in which of the above cases are the forces balanced? Well then, when the forces are unbalanced, we know that the forces in opposite directions do not cancel out. So which ones do cancel out? Let's take a look at number 1. The force the table is acting on the box, Fn and Fg, they are equal in length. They do cancel out, which causes this box not to move. So therefore resting on the table. As for the Mosquito, falling down at terminal velocity, the air resistance and the force due to gravity are equal, so that it is not accelerating, it is only moving at terminal velocity. These two cases, we have balanced forces, but note that you can have a balanced force, you can have balanced forces while still moving, and that is important. You don't have to be at rest for your forces to balance. And that is right there. I wrote it right there for you to see. You can still be moving at constant velocity. But what happens when the forces are unbalanced, such as in 3 and 4? We see that you have all of the forces pointing downwards for the phone, and that makes sense because imagine this phone moving upwards, it's going to decelerate as it moves to the top, and will start to fall down. So there's a deceleration happening here with the phone. As for the kangaroo sliding across the ice, he will or she will also be slowing down, decelerating. Now, when we have forces that are unbalanced, that means we have something called a net force. That means that if you add up all the forces together along a line, a straight line, these forces will add up, including directions. It will not be equal to 0. So Fnet will not be 0 when you have unbalanced forces. So that's when you add up all the forces on a body. Okay? So it's kind of like the leftover force. Okay? It's kind of what's left over after you've subtracted a bunch of things. You've subtracted a forward force with a backward force, etc. This is not going to make sense, probably, until you see an example. So I will see you for an example coming up, talking about how to apply Fnet and free body diagrams to a question. See you in the next video. Fat Mama Physics signing out.